Good morning, everyone. My name is Sisipho Dlakia. I'm a master's student at Nelson Mandela University, and I'm here with my colleague, Francois Swanepoel, who's an honors graduate student. We're going to talk about high-performance computer sensing for early warning systems in geological disasters. So we're going to introduce our talk, and then we'll take you through the framework we implemented for our study, and also talk about the algorithms we use for detection warnings, and introduce a case study with you and tell you how we're going to control the big data, and then conclude. Geological disasters are destructive events that occur because of certain processes that are occurring on Earth. They often lead to loss of life, economic cost, damage to infrastructures and properties. So their effects are that they lead to the loss of life and properties, and their examples include, but are not limited to, volcanic eruptions, landslides, and floods. On that side, left slide over there, we have a picture that was taken from Durban. We recently had floods. They disrupted the environment, the roads, and the infrastructure, and properties like cars and such. So early warning systems employ integrated sensors for monitoring and identification of geological disasters. They help to reduce threats to life. They help to avoid the economic costs and the damages to infrastructure and properties. The current sensing methods that are currently used are point sensors. And we present this study because we want to introduce distributed sensors, for example, an optical fiber sensor that we used in the field. The point sensors that are currently used have limited functionality, and by that I mean they cannot cover large areas. They are discrete sensors and they require complex connections. And what we introduce now are distributed sensors, which are sensitive along, it's an optical fiber sensor, which is sensitive along the cable. And it doesn't require any complex connections, and it covers several kilometers.
So we had a few key components. Mostly it's going to be related to the optical fiber which we used and we customized, which will measure the strain rate on the soil that it experiences over the course of an experiment. We also had a microcontroller which measured moisture, temperature and humidity over the course of an experiment. We built a small scale model which would simulate natural yield slope environments and would allow us to incline the body of soil to the desired tested slope angle. We also built this rainfall simulator which would precipitate the moisture on which would precipitate moisture on the body of soil in order to induce a mass wasting event. Our sensor distribution were mainly at the bottom of the slope, at the middle of the slope, and at the top of the slope. Our microcontroller was made in this fashion, and it would constantly measure these three variables. It presented it in an Excel spreadsheet, and over the course of an experiment, we would notice any sort of changes that the soil made, and to go and look back at what might cause this. In specific note is event 5. This is a mass wasting event. Even though it's small, it's of significant value. You can see that there was a big increase in the moisture content which led to this creation, while afterwards the moisture content lowered fairly significantly. Well, not nearly, but the humidity content is certainly rised. Now the optical sensor was used in this fashion, and it was, like I said, used so it can detect the strain that the soil experienced over the course of the experiment. I would like to draw your attention to the first graph. This is a signal we got for that mass wasting event before the event occurred. And which is of particular note is the soil represents hysteresis. So it increases in stress, and then there's a subsequent decrease in stress. This is related to the increase in moisture content and then subsequent decrease in moisture content, which ultimately led to the slope failure. This one is during the event. Notice that the frequencies are completely different, and this is due to the rate of moisture increase for this one, while the soil movement for this one. It's also of note that the amplitudes stay fairly consistent, so there's a certain minimum threshold required in order for a mass wasting event to occur. As you can also see that these S3 curves in the S3 direction of the fiber, the movement is of note, signifying that there's subsurface flow, subsurface water flow, and the slurry that is excreted out of the slope is moving in one specific direction.
So for a real-time example, we'd like to introduce the dam outburst of the Jagersfontein tailings dam storage facility. We regard that as a landslide because there was a mudslide which swept away the houses, it destroyed infrastructure, and people were forced to move. That all resulted to economic cost. It did not only affect the people who were staying there, but also the government as well. So we introduce the way of storing data, that a single point sensor that is monitoring over 24 minutes at 1 kilohertz, the size of the data will be 0.3 megabytes, right? And then if we monitor a facility like the Jagersfontein Dam with a 1 meter spatial resolution distributed sensor, which is the optical fiber sensor, the storage has an average perimeter of 250 meters. The data that will monitor there per day is 31 gigabytes per day. And that will be made possible by powerful processors and cloud storage. Now for data, we know that the sensors will monitor everything, but if we present that to customers or present it to people, we won't send all of that data. We will use machine learning algorithms like look, save, and throw away. And they will only focus on the data of interest, which is the one that will present the thresholds that will tell you that, okay, now your slope is failing, now you need to evacuate, and stuff like that. From all research that we have done, we believe that it is possible to use the high computer sensing to store data in geological disasters because the optical fiber records, stores, and processes metadata. And the high performance computing is required for real-time monitoring, and this application of the system that we're presenting offers geo-economic benefits. Thank you.